What is proscriptive and descriptive in epistemology?
Now, at this moment, it might be a good idea for me to describe why it's important that this is a proscriptive definition rather than a descriptive definition. If I go to a dictionary and I look up the word symmetry, I'll see a whole collection of examples of how the notion of symmetry is understood by regular people. And if I go and I talk to a mathematician, like if I were to spend some time talking to Richard as, what is the concept of symmetry? Or I were to go and talk to a physicist and I'd say, why is symmetry important to physics? Like, what is the essence of the concept of symmetry? Um, Forbid, denounce, or condemn. That's not quite right. Yes, in that sense, but it's the notion of proscriptive is again, I'm coming from a philosophical reading, which on one hand, proscribe, if I was thinking about it ethically, would be to forbid. But if I was thinking about it in the sense of a definitional sense, a proscriptive definition is essentially one that has a perfected, sharp boundary. So in other words, I'm distinguishing between the things that it is and the things that it is not exactly. It's proscriptive in the sense that I'm defining it in advance. So it comes from the older roots, proscribe. Pro meaning before or in advance of, and scribe meaning to cut a hard line, like a scribe. If I'm working in metallurgy, for example, or I'm working with tools, a scribe is a very sharp instrument, and when it scores the metal, that makes an irrevocable mark and a very precise mark. If I take I draw a line on a flat polished metal sheet with a razor blade, that line is going to be like really delicate and thin. And it'll divide the plate into what's on one side of the line versus what's on the other side of the line. The line effectively could be taken as infinitely thin. So the idea of scribing in this sense is to take that notion of perfected boundary to the extreme of mathematically precise. Delineate, yes. So in this sense, if I'm writing a piece of software, for example, I might say, in this program, I'm going to set this variable equal to this value. So the letter A equals 10, semicolon, right? And in that sense, the variable is going to have the variable 10 in this case. And there's no ambiguity. It's 10.0000, whatever, right? And in that sense, it's not 11, it's not 10.0001, it's not 9.99992 or anything like that. It's precisely 10. Whereas if I was describing it, I'd say, well, I only know it to be approximately close to 10. Right? Like I'm measuring something with a thermometer and I can only see, well, let's see, given the quality of my eyesight and how much I need glasses or something, I'm only going to say the temperature is probably between this number and that number, but where it is exactly, I don't know exactly. But in a piece of software, if I'm setting it to a number, I'm writing that number down in a discrete way. So the difference between observation and saying, I notice that these things look vaguely symmetric, to an expression, I'm saying this is what symmetry is really to refer to the difference of, is it a perception and I'm describing what I see? Or is it an expression and I'm telling you how I'm setting it up? So a proscriptive definition is I'm alerting that in a kind of mathematical sense, I'm defining this term explicitly so that I can use it formulaically. And this is a key move, because if I'm taking descriptive things and I'm trying to manipulate them in a formal logic sort of way, if I don't know what I'm manipulating, I don't know whether those manipulations can actually be done. Right? So for instance, if I have a proof and the proof depends upon 1 + 1 = 2, well, that only really works. The equality only works if it's exactly 1, another exactly 1, equal to another exactly 2. right? If it happens that the first number is 1.0001, but I only know the first part of it because the I don't have in my measurement enough to distinguish some of the fine numbers at the a good distance to the right of the decimal point, then it'll look like 1 plus 1 equals 2, but it won't actually be the case because it's really supposed to be that notion of trueness associated with the equality is because of the perfection of the idea of the integer being exactly what it is. So in this sense, if I'm trying to basically assert something in the notion of proof, I have to say it's not mostly the case. It's not mostly true. I have to be able to say it is exactly true. And in order to do that, I have to be able to say that something is exactly the thing it is, which means I need to switch from a descriptive way of doing it to a proscriptive way of doing it. So this notion of saying I'm going to define symmetry in this exact way is, on one hand, it's a hypothesis because I'm basically saying, well, does this way of defining the thing actually correspond to the way the word symmetry is used in the real world? And I'm going to assert that it does. And I can show that with examples. Then I can go a little farther and I can say, are there any counterexamples? Is there any place in the world where the notion of symmetry doesn't fit this underlying pattern that I have described exactly? And if it turns out that there's no example where somebody was using the term in a clear way, there wasn't an example of this underlying pattern, then we can make the claim that the proscriptive definition corresponds to the descriptive definition. So in effect, we could say that the meaning that we've given to the term is actually correct, right? I'm not making it up. I'm basically making an observation. Here's how the term symmetry is used in the world. Here's how I'm describing it proscriptively, and they correspond to one another, right? There's no counterexamples. And so in that sense, we therefore have confidence that our way of defining the term symmetry is good for the use of proof, i.e. that the semantic meaning of the notion is therefore semantically corresponding to the reality of the term in theories like physics and mathematics in the deepest possible way. And this is relevant because we are actually talking about things in the notion of comparison, which again is at the very deepest level, is the very foundation upon which epistemic process is itself known. Any theory of physics is known. Any theory of mathematics is ultimately known. Without there being both a absolutely clear sense that the semantic relationships are deeply held, it cannot not be held, and that the logic of the proof is in a sense strict, right? We need to establish both of these things as being true because, again, it's a garden path argument. It's what is called a rigorous argument. Again, it's kind of a joke in math, but they'd say a proof will convince a reasonable man and a rigorous proof will convince an unreasonable man. At this particular point, I need to basically show that it is for sure the case that the incommensuration theorem is a rigorous proof. And I know I'm sounding pedantic as all hell, but there's a clear example of I'm basically trying to show with a level of clarity as to not only what are the explicit moves that were being made, but why we are needing to make those moves. And this is a lot more detail than I originally wanted to do, but I'm realizing that the strength of the proof is literally contingent upon this sort of setup. So in that particular case, it's important to actually get a record of this.